Hello, welcome to the SUSECON Digital 2020 lab, securing your SUSE CaaS platform for environments. This is a set of hands-on lab that you can reproduce at home, and a demo that I will present to you today in videos. I'm Patrick Mass, and I work as Cloud Solution Architect in SUSE EME consulting team. This hands-on lab consists in 5 sections. We start with authentication with user management in Kubernetes. We continue with authorization in role-based access control. And we'll complement at pod level with pod security policies. On the network sides, we will further secure network flows with network policies and CILIUM. And we'll integrate the service mesh Linkerd based implementation in our platform. So what do you need to implement that at home? You need a SUSE CaaS platform, for example, 4.1 version, which brings you Kubernetes 1.16 distribution and kubectl commands. SUSE complements that distribution with, for example, skuba command lines, as you can see in the lab, that will be used for user plugin, with user login, and also multi-cluster bootstrapping, deployment, update, and upgrade. In terms of infrastructure, you need at least one master. You will have one in the lab. You will have one worker to have something interesting to play with. We will have 2 workers in the lab. And you need an external directory service, either Active Directory, OpenLDAP would do, but in the lab, I've deployed for you 389 DS directory server. SUSE CaaS comes with a powerful security framework that is really required to be enabled on production. There is a health of extension possibilities. For example, for authentication, you can either authenticate thanks to certificates, tokens, or via authentication proxy, or just enable HTTP basic authentication. In the first lab, we will authenticate with OIDC thanks to Dex and Gangway. SUSE CaaS implements Kubernetes role-based access control to further specify users' privileges. We'll play with that. We'll further understand how it works with the second lab, where we will create and update roles and role bindings, also based on a prepared LDAP configuration. A third level of security exists to further validate API requests on Kubernetes resources, admission control. Admission control is implemented by admission controllers, which intercepts API requests after authentication and authorization, but before actual Kubernetes resources change, in order to either validate the given request to the request, for example, pod creation requests on persistent storage, which can be fine-tuned to ensure data security, or to mutate the given request to the request, which means to dynamically transform the request in order to further enforce security rules or adapt to the environments. Or you can do both validation and mutation. In the lab 3, we will use pod security policies, which is one of the default admission controllers. And by the way, in the last lab, lab 5, we will use Linkerd, which implements another admission control mechanism, webhooks. Indeed, Linkerd use webhooks to enable dynamically their Linkerd proxies that is injected in your pod as sidecar containers. Besides user access control, you have network access control with network policies, which is used to further control your network flows. Network policies requires the use of network container network interface plugins, such as CILIUM, and that will be the goal of the lab 4. For lab 5, we will integrate a service mesh Linkerd in your role-based secured platform. In terms of architecture, you will find all Kubernetes standard components, starting with API server, controller manager, scheduler, or etcd database. Besides, SUSE CaaS brings the Skuba CLI, the network interpod network connection with CILIUM, and for the authentication, Dex and Gangway. This is just an example of SUSE extensions components that are brought in the platform. You see more here, Kurd, for example, or Tyler. Indeed, in this picture, I've depicted the lab setup that I've deployed for this demo, with one master, two workers, and one management node where you will find admission tools such as Helm or 389DS directory server. Besides that, the network setup is very standard as you will deploy SUSE CaaS Platform. Lab 1 authentication. Let's first understand further what is Dex and Gangway. Dex is an identity service which differs authentication requests to external identity providers thanks to connectors. We will see in the lab 1 the LDAP connector in play. Gangway is a web application frontend which is used to facilitate the authentication. It uses Dex behind the scenes. In terms of flows, the user simply connect to Gangway web applications for the login. And thanks to Dex and the external identity provider integration, kubeconf configuration file is generated and provided back to the user, which use it when using kubectl command lines. In a similar manner, but on the command line interface, using Skuba auth login, the user will get back his kubeconfig file that is specific to his user identity and use when you're using kubectl. And we'll use that during the lab and connect to the cluster and inspect the cluster while authenticated. Lab 2 role-based access control. In SUSE CaaS, two types of accounts are defined, either user accounts or service accounts. The first one, user accounts, are actually defined in terms of objects defined externally. In our example, in our lab, it's defined in the LDAP database. The service accounts is different. It's automatically defined, for example, when a new service is deployed in kubectl. On the other side, you have a set of capabilities, accesses to resources, operations on the resources that are defined in roles, either cluster-wide or namespaced. Those type of roles are connected, bound to the accounts, either user or services, thanks to cluster role bindings or role bindings. In SUSE CaaS, you will have default roles and default role bindings defined already for you. First, the cluster admin, which is used when first connecting to the cluster. We'll also use in the lab the admin cluster role that we will use to define the tenant admin that is that we want to restrict to a given namespace. The lab 2 then will be to exercise those role-based accesses with a specific set of users and new users defined for you and that you will define during that I will show you during the demo. Lab 3, pod security policies. As mentioned, admission control is a framework enabling to further secure security in your cluster. Pod security policy is one of the example of built-in administration controllers and is a way to control what a pod can do in the cluster depending on the cluster and service accounts who has launched it. So it works the following manner. So first you specify the set of privileges, access to volumes, access to allowed capabilities in your PSP that you configure in your role, either cluster role or just the namespace role, and that you bind to your user accounts or your service accounts. You will see that during the lab 3, where we will inspect the default PSP and then we will define specific PSPs to enable user-specific accesses to your resources. Lab 4, network policies. Network policies concepts enables us to really master network security, implementing a sort of firewalling in your cluster. So it's important to know that per default in Kubernetes, all pods can communicate between each other. This means that a pod can receive traffic from anywhere and send traffic to anywhere. We want to restrict that in production. Internal to the cluster or with the external world with ingress and egress rules. This is thanks to network policies that you can do this. In this picture, for example, it's an example where, for example, you have an application with is 3-tiered with a web front end, an application server, and database, where, for example, you want to restrict the accesses between the web front end and the database layer. In a similar manner, you would want to restrict the external network accesses only to your web front end and not directly to your application server or your database. There's a lot of implementation of network policies in terms of a code that comes in your Kubernetes container network interface plugin. First, CILIUM, which is included per default in SUSE CaaS, but you may know about Weave or Calico. A full list of CNI plugins can be found in the link here. The CILIUM CNI plugin is a very interesting one. It delivers really an efficient network packet processing alternative to IP tables, thanks to Linux Berkeley packet filter, which implements Linux kernel-based packet level filtering at level 3, 4, or 7. Allows you to really go further than pure IP address-based security. Interesting to know that you can dynamically change the rules transparently from a user standpoint. So all this can be done on the fly without any impact on your pods and your containers. We see that during the lab 4, where we'll restrict incoming and inter-pod flows thanks to network policies. Lab 5, Service Mesh. Service Mesh is a dedicated framework meant for inter-application communication management. It's very important when it comes to microservices, cloud-native designs, where there's a lot of interconnected services, which implies complex network flows, network and security challenges, and very complex to manage. So we need to have an implementation of a service mesh such as Linkerd that is used in the lab, which implements inter-service resiliency, timeouts, retries, load balancing, metrics, tracing, service discovery, or routing. All this transparently to the services, to your app. So very interesting to to leverage, and we will see that in the lab 5 where we integrate Linkerd service mesh service in our secured platform. And now this is time for demos. Please have a look at the set of videos coming along with this presentation to have a quick view on how this works and how to produce at home. I hope that you have enjoyed this presentation, and thank you very much for your attention. Hello, welcome to this intro demo part of the SUSECON Digital 2020 hands-on lab, securing your SUSE CaaS platform for environments. Overall, this demo video set is divided in 5 separate labs. Lab 1 will demonstrate you authentication and user management in Kubernetes. Lab 2 will demonstrate authorization with role-based access control. Lab 3 will demonstrate pod level admission control with pod security policies. Lab 4 will demonstrate network flow securization with network policies and CILIUM. The last one, Lab 5, will demonstrate security mesh and Linkerd security. There's a number of ways to secure platforms such as Kubernetes clusters implemented with SUSE CaaS, either using embedded Kubernetes features or adding more to it with plugins, operators, etc. The intent of this demo is to lead you through a set of handy standard security related features that are very important to master before moving to more advanced implementations. So in this video, I will show you briefly how the lab is composed with to let you reproduce at home. As presented during the first presentation video coming with this session, we have 4 virtual machines, 1 management, 1 master, and 2 workers. Each virtual machine has 2 CPUs and 4 GB of RAM. The amount of storage depends on the virtual machines. So as an example, in this demo, I've used 50 GB, 40 GB disk for the management, 50 for the master, and 100 GB for each of the workers. Let's now connect to your cluster via the management nodes. The first thing is to go to the My Cluster repository folder, which is with knowing that My Cluster is the name per default selected to identify your cluster when you are deploying SUSE CaaS platform. Let's have a look at your cluster status. As you can see, we have the 3 nodes here already, all with SUSE Linux Enterprise Server 15 SP1, running Kubernetes 1.16 version. And on the right, we have the exact version of the CaaS platform installed, which is 4.1.2. Let's now have a look at the pods that we have deployed in kubesystem namespace. As you can see, we have the standard Kubernetes pods here. The API server, controller manager, scheduler, etcd database. In complement, we have the CILIUM that I mentioned. We have the Dex and the Gangway. I've already deployed the Tyler pods, which is required for the Helm-based deployments. Let's see now with which user we are connected to this cluster. For that, we go to kubectl and we have a look at the config, which is already loaded. Here we see that the current context here is Kubernetes admin at my cluster. In this cluster, we see that we have a cluster named my cluster, which is the same name as the folder in which I'm running, okay? And the user is Kubernetes admin. In a later stage, in the lab 2, actually in this demo, we will demonstrate to you what type of role and privileges this Kubernetes admin has. As you can imagine, he has all the rights on all the cluster objects and operations, basically. The credentials of this Kubernetes admin is in home.kube.config. So we can have a look at it to have the more details about what is currently set up. That's where we have all the details in terms of client certificates, data, and the key that is currently set up for this Kubernetes admin user. All this is set up for you when you are deploying SUSE CaaS Platform. So let's now, at last check of this introduction video, let's check quickly that we are connected to an external LDAP that I've set up for you. Here we go. We see that there's a number of users that are already defined here. Okay, user 1, 2, 3, and so on. Okay, and a set of groups that we will leverage in the other videos of these sessions. Thank you. See you in the next video, the Lab 1 Authentication. Hello, welcome to this Lab 1 demo, part of the SUSECON Digital 2020 hands-on lab, securing your SUSE CaaS platform for environments. In this video, I will show you how the LDAP server implemented for this demo with 389 DS server is set up, the current users that are already populated in the directory with the groups, how to add a new user in the right groups, and how to use this new user for authentication and kubeconfig configuration. For that, we are connected to the management node here and with the right directory in the my-cluster directory, which corresponds to the cluster name. So first, let's check if our LDAP server is running as a container with Docker PS. This is the case. Now let's look at the contents, for example, with the users contents, with the LDAP search command using object class equal person as filter. We see that we have a set of users, -1, -2, -3, and so on, that will be useful for the remaining of this demo. Let's have a look at the already configured groups using this command. As you can see, we are using object class equals POSIX group as filter. And we see that there's three interesting groups for the demo: Kubernetes-users, -dev, and -admins groups that already defined with some members there, which is quite interesting for the user group mapping, as we'll see later on in this demo. In the following of this demo, we would like to base authentication and authorization on groups, not on users. And as a matter of fact, to enable this group-based authentication and authorization with Dex and Gangway, we need to make sure that some prerequisites are fulfilled before. So the first prerequisite is at the Kube API server level, the way Kube API server has been started. And for that, we need to inspect the pod, the API server pod, with this command, kubectl describe command, where we will look at the OIDC related starting arguments for the API server. And what we want to see is this field, OIDC-groups-claims equals groups. That needs to be included there. And as a matter of fact, it is done per default by SUSE CaaS Platform. So we are fine. The first prerequisites is fulfilled. And since we are here, it's interesting to also note another thing, is this field, OIDC-username-claim, that is equal to email, which means that we need to use email as login ID when we are logging in. And we will see that later on when we will log in, either on the web interface or on the CLI interface. So this is the first prerequisite. The second one is on the way Gangway has been started. And it needs to be started with the right scope. The Gangway scopes is defined in the Gangway config map named oidc-gangway-config. And what we need to look at is the presence of this field in the groups table. It's the case here, and it is also done per default in the SUSE CaaS platform. So it's important to have to make a note on that. Third prerequisite is not done per default because it depends on your environment and on the way your LDAP has been set up. It relates to the way Dex pods are started and configured. And you need for that to inspect and to maybe change the Dex config map. In this config map, you need to look at two fields, the user search and the group search. The first field, user search, is used to make sure that a given user exists and can be authenticated in the LDAP server. For that, Dex will use this objects class equal person as filter. As we have seen when I've done the LDAP search by hand, which is actually exactly the same as what is done by Dex when trying to authenticate a given user based on the external LDAP. We know that that works. So our filter is good. On the group search, we are using another filter, which is this one. I've used the same when I've searched previously the groups in the LDAP server. So we know that works. This is not it. We need to make sure that the users are really mapped to the right groups. This is done here, thanks to the user attributes and the group attributes. The DN field of the users needs to map the content of the member field of the groups. For example, if you look at user 2 of in the existing LDAP server, redoing the same command as before, this LDAP search, we look at user 2 and the DN field is this one. Okay. Let's try to remember this one because now we will look at the groups and we look at the members of those groups and we would like to ensure that we find this DN field. Here we are, here it is. So I think we are fine, and the user 1, -1, -2 and -3 and others are well defined for this user group mapping. This is important when we will create a new user in the same manner in order to make sure that the new user are well mapped to the right groups. In case you need to change the Dex config map, you can do that right away by editing the Dex config map with the capital edit config map command. You do that by doing this, which open in VI the config map where you can do the change. In our case, we know that it works well, so we don't need to do anything. But again, if you have done some change, you will need to do two things to restart the Dex pod, for example, with this command. Okay, that will delete all the Dex pods. That will be restarted automatically. It's not required here, so it's not. Let's go on the next step. And also you need to delete the Gangway pods with a similar commands, which is this one. And in a similar manner, automatically the Gangway pods will be recreated. Okay. Let's now create a new user 4 in the LDAP server. For that, for example, we can do this, creating an LDIP file with some prepared fields where you can see very similar fields as defined for the other users. Okay, I'm using the same organization. Okay, and the same email and so on. And I've prepared a special string here in which I will include SSHA hash corresponding to the actual user 4 password. And I will include that in the LD file with this command. This SSH hash is created by, you create it by different commands, but here is an example of a command that will work. The slap password command that will create that for us. We can check the value of that by looking at the contents, the new content of the LDIF file. Okay. Now let's add this new user in the LDAP server. This is done with the LDAP add command this way, and we can check now the LDAP with the LDAP search. Or is the same. And here we are. We have the user 4, but we would like to have this user 4 included as member in the Kubernetes-users and -dev groups. For that, I've created a LDIF file for us, where I'm modifying the existing groups. The first one is being Kubernetes-users, and the second one Kubernetes-dev. I will modify to add each time a new member, being the new user 4 DN field, because we know that this is important because used for the user group mapping. Let's add it using LDAP modify command line, just as this one, applying the new LDIF in the LDAP. We can check that just after that, doing an LDAP search. Okay, indeed, user 4 is in Kubernetes user and Kubernetes-dev group. Now we would like to use user 4 to log in ourselves for cluster access. And first we will use the web interface, the Gangway web interface. So what is the right URL for that? It can be found by looking at the Gangway service. With this command kubectl get services, you'll see all the services, including the Gangway one, where you see the ports to be used, 32001, and we see that it's a node port, which is okay for demo, but not okay for production, because in production you will need to have an external load balancer to access your this type of ports. In this case, since it's a node port, we will use one of the IP addresses of our nodes. Actually, we use the master node IP address plus the 32001 ports to access our Gangway web interface. So I'm reloading the web interface to show you that it's up and running. I click here to sign in, and then I will use user 4 and the password to log in. So we are authenticated, and as you can see, we have two ways now to continue to and to acquire um, the the rights to connect to the Kubernetes cluster, either by downloading the config file or by copy pasting those commands and executing them on your command line. Let's download the kubeconfig directly. And we retrieve it and rename it in such a way that we can use it right away with kubectl. Okay. And we use it with kubectl, for example, by using this type of command, telling kubectl to use the new file that I've just downloaded when doing an operation. For example, looking at the pods in the user dash namespace. Here we go. We have the results, and we are seeing some pods in this user dash namespace. So that works. User 4 is well authenticated to see the content of some contents of the Kubernetes cluster. On the authorization side, we'll see that later on. Now that we have used the Gangway GUI, we would like to test the command line interface, which is the second way to see to authenticate ourselves as a user. For that, let's use user 3 for the CLI based authentication, and we will access directly the Dex Gangway, the Dex service. So we need to come back to the services, and this time I would like to look at the Dex service, which is similar to the Gangway but with a different port, which is 32000, and it's also node ports. We use also a master IP address, for example, a master node IP address to access these node ports. Again, it's a pure demo like setup. For that, we can use skuba auth login command, such as this one, where we are connected using again the email of user -3, the password, and the master node IP address colon the ports corresponding to the Dex service. We have downloaded automatically a file named kubeconf.txt that we will rename for user -3. And let's try to use it right away as before. To connect to some to make sure that is well authenticated. So I'm doing the same. I know that user 3 can have access to the user dash namespace scope. So that indeed works. So to authenticate the other user, you do simply the same. And Skuba auth CLI is actually the easiest way to do that. And we can do that in one command. Like this one for user 1. Okay, it's already removed. The kubeconf.txt file has been already renamed for user 1. We do the same for user 2. It's not really required, but we can do that for user 4 as well. And if you want to just check that it's still working, we can do that and the kubeconf will be very similar as the one downloaded from the Gangway GUI. Works exactly the same way. Just has been regenerated, basically. And we can do that for the last command being user-admin. Okay, so everything is okay for all the users. Now what is interesting to see is what is exactly accessible from to these users. So we can dynamically, and for that we need to apply the right security context. So first I've dynamically loaded the user specific kubeconfig in the kubectl command. So this is a way. Another way is to use the kubeconfig variable and to export it with the right value in order to have an easier way to switch between contexts. I will see just right away. So first, I think it's a good practice to save your kubeconfig in another variable and to export it, to export the new value. For example, this one where, as you can see, I'm redefining, so I'm reusing the Kubernetes-admin config, which is the one that has been set up during the deployment of the platform, and the new kubeconfig files that I will merge in a one same kubeconfig view, basically. This can be checked after this exports with doing a kubeconfig view, kubectl config view, where we see everything that is loaded in a given context. So we see that we have still two contexts: the existing one, the one that we are using for the admin type of accesses, and my local one, which I will use for the user-related access to the cluster. Here we see that the context is still being the one having the administration rights, as we'll see in the next lab after this one. What is important here is that not only we have the existing Kubernetes-admin users loaded in this context, but you have the new users, user 1, 2, and so on, that are loaded with the right certificates, ready to be used to access to your environments. And this is done, for example, by setting up the context to switch by switching the context as follows. Let's set the context to user 2, for example. This is done this way. We are setting the local context to the cluster local with the user 2. And let's now use it. So, pset cuttle config use context local. Okay. Now, when I'm doing kubectl get pods, for example, comments, I will act as user2. Let's do the same as before. We know that works because user2 seems to have access to a user namespace. Let's retry that. Okay, works. But does user2 have access to the default namespace? No, seems not. Okay, that's interesting. And we'll see in the next lab why is the case. Okay, so now we have several users login, authenticated, but they are not authorized to do everything. So what is interesting from a security standpoint is that we can restrict accesses per default, as we see here. And user must be explicitly authorized for a given set of operation on a given set of Kubernetes resources to have access to those. You see that in the next lab, where we will manage those authorizations thanks to role-based access control. So for this, thanks to go to the Lab 2 video, and thank you very much for your attention. Hello, welcome to this Lab 2 demo, part of the SUSECON Digital 2020 hands-on lab, securing your SUSE CaaS platform for environment. In this video, I will show you how to manage authorization thanks to role-based access control, and how to group them thanks to LDAP groups. For this, I'm connecting to the management node to my cluster, and I would like to understand what is the default user that has been created per default when I first installed my SUSE CaaS platform. For this, I'm looking at the current security context. This one is named Kubernetes-admin at my cluster. It's a context that is defined for the user named Kubernetes-admin. This is my default user. Now, what are the default capabilities that has been allocated to this user? To figure out, we need to look at the cluster roles that are defined currently on my cluster. And let's see the admin related ones. And we see that there is a cluster-admin cluster role. This is one really of interest. Let's figure out the details. And we see that you can do anything, any verbs on any resources. Now the question is to understand to which users this cluster role has been bound to. For this, we look at the cluster role bindings. Also looking at the admin related ones. And we see that there is a cluster-admin one. This is the one that is of interest. Looking at the details. We see that indeed is binding the cluster-admin cluster role to a group named system::masters. Now the question is our default user named Kubernetes-admin indeed included in this group? To check that, we need to look at the certificate that has been used to authenticate this user. And this certificate can be found per default in this home directory.kube config file, where we see the user, Kubernetes-admin, and his certificate data and his key. You see that it's base64 encoded. So we need to extract the certificate and to analyze that to find out about the group. This can be done this way. extract the value of certificate, the client's dash certificate data that is included in the config. We have put that in a file, as you can see here. Now we can decode it and create a certificate that can be analyzed this way. Okay, decoding it. And now we can analyze that, for example, with OpenSSL. And we look at the subject because we are interested in the group which is included in the subject part of the certificate. And we see here that indeed Kubernetes-admin user is included in the system:\masters group. And that's the explanation, that's proof that Kubernetes-admin have all the capabilities on our cluster because he has allocated the cluster role cluster-admin. Now let's have a look at our users. For this, we have merged all the configuration in order to switch between security contexts. This can be done by setting up your kubeconfig variable to all your kubeconfig configurations, like this one. Those ones has been created in our previous lab video. You can now set up your security contexts, one named local, to, for example, user 1 user. And we can switch to it by using this command. Now I'm acting as user 1 user when I'm doing kubectl commands. For example, if I do kubectl get pods, this will be done really as user 1. And actually, is forbidden as expected because there's not yet any binding, role binding or cluster role bindings to this user. Per default, when you are creating a new, allocating a new user in your platform, authenticating them, you need to ensure that there is a binding, either a role binding, a cluster binding that will point to this user or to a group including this user. Let's, for example, consider that this user 1 will have the same capability as our default user. So we need to create a cluster role binding to this user 1, pointing to the cluster role cluster-admin role. And in order to do that, we need to come back to my default Kubernetes-admin context. And now I can create what I wanted to do, which is, for example, a cluster role binding between the user 1 and, for example, this cluster-admin cluster role. Okay. If I switch back to the local security context, like that, I can now do whatever I want. For example, I get pods in the default namespace. Okay, but actually it's a bit too much for these normal users. What I would like to do is to restrict the users that I've created so far in the previous video to a special namespace that I've created for this demo named user namespace. To remind ourselves what are the groups that are defined in the LDAP, let's search it with, for example, this command, LDAP search command. And we see that we have Kubernetes task user group that has been defined here, which has already a set of members defined here, the user 1, 2, 3, and 4. Okay. let's create first a role that will be namespaced, providing some capability on resources, pods, and config map. As you have noted, I'm still user 1 here, which can do indeed this operation. But it's best to switch back to the Kubernetes-admin user for this type of operations to make sure that we can do that. Now let's create a role binding the role that we have just created to the group, the Kubernetes-user group. This can be done with this command. Now let's set the security context to, for example, one of the member of the Kubernetes-user group, user 2, for example. We set up the context like that, and then we can switch the context with this command. Now I'm acting as user 2. And what you can do is using kubectl auth cani commands to find out what you can do. For example, this one in the user namespace should work. As you can see here. But if you do the same on the default namespace, this will not work. If I do that on another resource, say ingress, this will not work because, as we have seen, we have provided capabilities such as get capability only on pods or config map. If I set the context to another user, to a user that is not in the group, such as user-admin, let's do that right now. Set the context to user-admin. Okay, we are still using the local context, but I've changed the local context with this new user. So now I'm using the user-admin user. And if I do the same checks, for example, doing this, trying to check if I can get the pods in user namespace, this is not possible because user-admin is not in Kubernetes-users. First reason. And second reason is that there is no binding at all actually created yet to this user. Because the intent is to use this user-admin as a tenant admin restricted for this namespace, user-namespace. And this can be done by binding the user-admin to an admin type of role. In order to do that, we need to switch back to our cluster-wide administration role, which is back to this one. Now we are back acting as Kubernetes-admin user, which has all the capability on the cluster. And what we like to do is to create a binding to this user-admin. This is done, for example, doing this, where I'm binding the user-admin to the cluster role named admin. And as you can see here, I'm not using the user, I'm using the role, the group. And the group named Kubernetes-admins, where we know that the user-admin is included. This way, we are allocating the user admin, which is included in the group Kubernetes-admins, to the cluster role named admin. And this admin cluster role is really created per default for this type of usage. We can look at the details of this role here. Which is defined a bit differently compared to cluster-admin because it's meant for namespace type of role bindings. So now with user admin user, we will be able to do anything but only on in the user namespace. So in order to check that, we need to set the context with user admin, switch to this local context, and figure out if we can do the operations such as get pods on the user namespace. Okay. Get ingress. It's okay. But if I want to do that on the, say, default namespace, this will not be possible. I can check that. You can be sure that user-admin is really restricted to the user-namespace here. This way we have created authorization that are namespaced for the group named Kubernetes-users. We have created a role for them. We can create other roles. We have created a tenant admin that are restricted to the user namespace. And we have first checked out what is the default user that has been defined for us when deploying the SUSE CaaS platform, and we have find out how the authorization has been meant for this default user. Now it's time to look at how pod level administration control is done thanks to pod security policies. And for this, please go to the Lab 3 video. Thank you very much. Hello, welcome to this Lab 3 demo, part of the SUSECON Digital 2020 hands-on lab, securing your SUSE CaaS platform for environments. In this video, I will show you what default pod security policies are set up in SUSE CaaS Platform and how to leverage this capability to further secure your environments. For this, I'm connected to the management node of my cluster. And first thing that you would like maybe to check is what are the admission controllers that are enabled in your environments, including pod security policies, making sure that it is indeed enabled. For that, you need to check the way the kubeAPI server has been launched and looking at the command line that is being used. And more precisely, this enable admission plugin parameter, which lists all the admission controllers that are available in your environment, including pod security policy. As a matter of fact, during the bootstrap of this environment, two PSP has been created for us, one privileged and one unprivileged. The first privilege will be used only for kubesystem type of pods. I will see just after that. The other one will be available for anyone. Indeed, it is very, very important to have at least one unprivileged PSP available in your environment. Otherwise, no pod can be launched because no PSP will be available for the given pod. As mentioned during the presentation part of this online hands-on lab, once specified, the PSP needs to be connected to a role, either namespaced or cluster role, and then the role is, as you know, bound to an account. So to understand who can launch the privileged PSP or who can launch the unprivileged PSP, we need to follow this path. So starting with the privileged PSP. The privileged PSP is usable the use of the privileged PSP is configured in the cluster role named SUSE CaaS PSP privileged, as we can see here. The users that are bound to this role are actually namespace, and namespace to the kube system namespace, as you can see here. So it's a role binding that is defined. As you can see here, that means that any authenticated and service accounts in the kube system namespace will be able to launch a privileged pod. What about the unprivileged pods, the unprivileged PSP? To follow the same path, we start with the cluster role named SUSE CaaS PSP unprivileged. This is the one that can use the unprivileged PSP. In terms of binding to the roles, we look at the default cluster role binding, which is the SUSE CaaS PSP default, where you can see that any authenticated service accounts will be able to launch an unprivileged pod, which is what we expect. Let's check that with, for example, user2 user. Let's first set a security context using user2 and switch to it. I've prepared for this demo a BusyBox pod that is unprivileged. Let's create it in the user namespace, because as we know, user2 has only access to this user namespace. And to figure out which is the PSP that has been selected for this pod, you need to inspect it and look at the annotation parts, where we see that the PSP that has been selected is indeed the unprivileged one. Let's now delete the pod because we will reuse it during this demo. We would like now to create a custom unprivileged pod security policy in order to fine-tune the way the unprivileged pods will access to Kubernetes resources. For this, we need to switch back to our cluster-wide administration user, the Kubernetes-admin. Here we go. And we will use a PSP that I've prepared for us, which is this one. As you can see, it's an unprivileged one. Let's create it. And now we need to have a role that will use this PSP. For that, I've created this role. We will use this unprivileged custom PSP. Let's create it as well in the cluster, like that. Now we need a role binding in user namespace because that's the one that we're using during these demos. With, for example, this command line, where, as you can see, I'm binding this unprivileged PSP to two groups, Kubernetes users and Kubernetes dev. As before, you can either bind to users or to group. I'm selecting groups. Now, if I switch back to the user 2, like that, I need to switch back to the right context and recreate the BusyBox in the user namespace. Now let's see what is the PSP that has been selected when launching this new pod. We look at the annotation and we see the unprivileged PSP, custom PSP that we have just created. So this is exactly what we wanted. Okay, this unprivileged PSP for now doesn't do really anything. We can further, let's say, fine-tune the way it access volumes, or we can try it out. That maybe let's figure out if what happens if actually it's a privileged PSP and not an unprivileged one. Before going further, I want to redelete my pod, and I would like to fine-tune the BusyBox definition in order to let's say consider that is privilege, and let's see if I can create it as user2 in the same namespace, user namespace. You cannot, because indeed there is no PSP that can be selectable for this user. There's no binding to a privileged PSP. This is why a user2 cannot launch a privileged pod such as this one. So this is exactly what we wanted to do, to ensure that to enforce only the capability to launch privileged pods to only the right ones. In this example, the users that have access to the kube system namespace. So in this lab, we have touched how we can leverage pod security policies to restrict the access to resources and capabilities to when launching pods with the right users. And as you see, this is done with explicit role binding. Now let's see how we can control network flows within pods, or from ingress or ingress external network to pods endpoints. This is the subject of the next demo in this series. So thank you very much, and let's see you in the next demo. Hello, welcome. This is the Lab 4 demo, part of the SUSECON Digital 2020 hands-on lab, securing your SUSE CaaS Platform for environments. This demo is divided in two parts. The first part, it's about inter-pod networking control. And to demonstrate this with network policies, we will leverage the multi-pod application WordPress consisting in a web frontend and a database backend. For the second part, about external access control, and to show how to secure external ingress accesses with another application, Kibana, and network policies, we will use a multi-ingress controller setup to separate admin-related flows from non-admin related flows. And for this, I'm connected to the management node of my cluster. I will start by setting up the context to be acting as user admin of my namespace, named user namespace. I will switch to it. It's named local, okay. And I will have a look at the pods in the user namespace. As you can see here, both the frontend and the backend database seems to be running. So I would like to check if it's indeed the case by accessing the frontend. And this is done by looking at the ingress that I've prepared for us and implemented by an Nginx ingress controller. If I look at this ingress, I see that the URL is mentioned here. So we are ready to try to access to this. We can do that with the browser, reloading this page, making sure that we have access to the application, and we can also do a wget because that will be quite handy later on when we will continue the demo. So as you can see, we have access to the application and from the external standpoint, and we have also an inter-pod networking that works between the front end and the back end. Without that, as we will see later on, the application will not work. But we would like to further control the flows that is going on. And a way to do that is by starting by denying all the flows and then to allowing just the flows, the exact flows that we want to re-enable. For this, I've prepared a network policy to deny all the flows. Here it is, where you see that we are selecting other pods in a given namespace, user namespace, and for them, I will do nothing in terms of ingress or egress. If I apply that, I will be able to check if that works. But before checking if that works, I would like to look at the CILIUM side and to figure out if CILIUM has enabled these network policies. For this, I can have a look at CILIUM endpoints, still in the user namespace. Remember, I'm acting as user -admin. So I need to add this capability to get CILIUM endpoints for user-admins. So to do that, and we know that since lab 2, I need to switch back to my master user by doing a use contexts. And when I'm back to my super user, I can create first a role which will be capable to do a number of operations, including lists on the CILIUM endpoints, and create a role binding, still using the group Kubernetes-admins, where we have the user-admins included. And this way, and you have to do that only once. If we come back to the local context, where we have user-admin, I will be able to get the CILIUM endpoints. And here, okay, indeed, I see that for all the pods, and especially the pods that I'm looking at right now, which is the WordPress frontend and the MariaDB backend, the ingress, both the ingress and the egress are enforced by CILIUM. So I should see that my URL should not be accessible anymore. If I do this with a wget, I see that indeed the service is temporarily unavailable. So actually, not only the front end is not accessible, but the front end has crashed because it's a dependency. It has a dependency on the backend. If we look at the pods, we see that the front end is not running and actually is kept being restarted. We can have the details by looking, for example, in the logs of this pod. We'll see where it is at the moment. And here we see that he has, for example, failed after 36 tries to connect to the DB, which is as expected because we have denied all the traffic, all the flows in this namespace. Now we need to re-allow the right flows. For this, we'll start from the MariaDB standpoint, pod standpoint. And for this, I've prepared a network policy, which is this one, which is applied on all the pods matching the MariaDB app. And from this pod standpoint, it will allow ingress traffic coming from pods matching the labels WordPress, which correspond to the front end. And this ingress traffic would be allowed through this 3306 port. Let's apply this one. And have a look at the CILIUM endpoints. We still see that there's no so much change here. As soon as we have applied the first deny all network policies, all the pods in the given user namespace has been, let's say, concerned by the network policies. That's why the enforcement is true for all the pods in the network in this namespace, user namespace. So no change here, still enforced, and because of both the deny and the last one that I've just created. If I look at the network policies that are applied at the moment, we have the two ones, deny and the one we have just created. But this will not be enough because we have the front-end pods on which we need to also allow the capability to send egress traffic to the database. And for this, I've created another network policy, which basically from a WordPress app standpoint will allow any ingress and any egress. Let's create it. Here, looking at the network policies, we see that we have 3 network policies at the moment. And we can have a look at the pods to make sure that all the pods are up and running, because that takes some time. Because as we have seen, the front end was were kept in this crash restart loop. So we need to make sure that first the front end is back in active mode, and then we will retry to access the URL. Can have a look at the logs as well. So we see that it's currently reinitializing itself. Takes a few seconds. Again at the logs to see where it is. Okay, that should work now. Okay, it's running. Now we can do a WD gets again. Here we go. We get the index.html. That works. We can have a look at the reloading this. Okay, we see that we have access to the API, the web application. So I've started by denying all and then re-adding the flows that I wanted. So that works quite well. And that's end the first part of this demo. And before moving on, I would like to delete the network policies that I've created. And we'll look at the other application. Okay, so with that, we are back to normal with no network policies in the user namespace. What we would like to do is to restrict access to an admin GUI such as Kibana for only admin-related flows. For this, we are leveraging the ingress controller and a special setup with 2 ingress controllers. This has been, for that, I've prepared 2 ingress controllers that have been deployed in the environment. And in order to see them, I need to have the capability to access another namespace. So I need to switch back to my super user, which is Kubernetes-admin. Once here, I can have a look at the kubectl get pods in this nginx.ingress-ingress namespace. And here I will see indeed 2 admin controllers, so 2 ingress controllers. The one that would be, let's say, the classic one for non-admin flows, and the second one is meant for admin-related flows. Let's have a look now at the services that those those 2 ingress controllers are exposing. We see here that in this example, this first ingress controller is, let's say, placed on the master node IP and the worker 1 IP. And the last controller, the one that will be meant for admin-related flows, are served by the third worker. This is an example just for this demo. But it's interesting to know how the flows are physically, from a L3 layer 3 standpoint, separated. Now we will look further into the details on how I've enabled this separation of flows. This starts by the way I've created those 2 ingress controllers. So we will look at the details of the first one. Which is here. So this one will correspond to, let's say, the classic ingress counter that would be deployed if you follow the SUSE CaaS Platform and the Nginx documentation. So you see that starts with the ingress class. This means, so that's a classification, a categorization that is used by the ingress controller that you are setting up when you are starting the ingress controller. So here, this is just Nginx, which is the value per default. That's the first thing. The second thing is the labels. As you can see here, and this is done per default, The components label is set at controller. This will be a bit different for the second admin controller, the ingress controller. If you also inspect it, we'll see that, and this is something that I've done on purpose. I've set the component label as controller-admin, and I will have set up the ingress class as nginx admin. So the purpose of those changes is that the ingress class, a different ingress class, will enable the possibility for a given pod, a given service, to select the ingress controller that will be serving the given service. As you will see, for the Kibana service and backend, I will configure two ingresses, one for the normal Nginx controller for the non-admin related flows, and the second one, a second ingress that will be specifying an ingress class in the annotation to make sure that it will be served by this other ingress controller that will serve the admin related flows. So that's the purpose of the first change. The purpose of the second change in terms of label, is to make sure that to ease the configuration of my network policy, because the second step is to restrict the only the accesses to this Kibana GUI backend to only admin related flows. So I will only allow network flows coming from pods, the ingress controller having this label. So that will be quite helpful later on. Let's see how that works by looking at. So we now have seen the user namespace, pods. That's everything that works. And now, yes, we need to have a look at the services, the backend services, especially the Kibana one, because this is where I need to access finally. And as you see here, now I'm looking at the user namespace services, the application ones. As I mentioned, we need to have two ingress specified for this Kibana endpoints. We will have a look to them, and as you see here, I have a Kibana ingress and a Kibana -admin. Let's look at the first one, and we'll see how it has been specified to make sure that it will be served by the normal non-admin related Nginx ingress controller. This is done thanks to the annotation. Here we are specifying the Nginx that we want. As you see, this is only the Nginx here. If we look at the other Kibana ingress that has been specified, I've changed the annotation so that I'm ensuring that it will be served by the other Nginx ingress controller. So that's quite easy to do and can be really systematized, done in a systematic manner in your environment. Now we will try to access our Kibana internal endpoints using, for example, curl, which is quite handy to make sure that we are addressing the right path. Here I'm accessing the non-admin related ingress, so URL, as you can see here, that will be served by this non-admin related Nginx ingress controller. And we see that we access the Kibana server. By the way, in this demo, the Kibana server is responding. That's what we want, but it's not ready yet because the Elasticsearch behind the scene is not up and running. But that is fine for this demo. What I want is to have just a Kibana server that is replying to us. In a similar manner, I can explicitly access to the admin URL, which is this one, that is served by the second Nginx ingress controller. I see that works well. But if you mix the things by, for example, trying to access this URL, but based on the first ingress controller, the one that is non-admin related, I will have the default backend. Similarly, if I do the opposite here, accessing the test local, but via the admin URL, I will have the default backend as well. So here, I've demonstrated that we have a clear path, so still both paths between the non-admin related Nginx ingress controller and the admin related Nginx to the same backend served by Kibana. Now what I would like to do is to restrict one of the paths. I will restrict the non-admin related flows. This can be done by a network policy that I've prepared that will select for the pods matching the application Kibana. So that's on my backend. Only ingress traffic coming from the controller admin. That's how I'm using the specific label, component label that I've set up for the second Nginx ingress controller. And I also will double check that with a namespace selector being the Nginx ingress. Let's apply this one. And actually, without having to deny all, because here I have only one network policy, but that address the Kibana, it's enough to make sure that I've still have access via the admin path, but I do not have any more access via the non-admin path. This one will time out. So this is the way, thanks to our network policies, to really enforce one path, for example. We can have a look at the CILIUM endpoints, by the way. If we look at the CILIUM here, we see that since I've removed the deny all and only have a network policy that is applied to the Kibana related application, only the Kibana has the enforcement. And as we have seen in the definition of this network policy, I have only a policy type, which is ingress, which is the reason why the enforcement is only on the ingress side when I'm looking at the CILIUM. So we have done what we wanted, but that's quite interesting to also have a look at really, when you are adding a new network policy, thanks to CILIUM, it's possible to make sure just to try it before, let's say, deploying that further down the road. And if you want to troubleshoot the way you are writing your network policy, you can write CILIUM right away, as I will show you. So first, that's really a very interesting troubleshooting tip. Let's have a look at the pods, and we have the CILIUM pods, because what we will do is we will execute command on the CILIUM pods, and we will simulate the execution of the given network policy. So it's a rule that he will try it for us and will tell us whether it's denied or not. For that, I need to know what are exactly the CILIUM pods that are running in my environment. I need to also have a look at my sources and my destination. And the destination will be the Kibana one. And the Kibana is in the user namespace here. Once I have the source will be this one, and the destination, I can do the policy simulation by executing the following command on one of the CILIUM pods. Executing actually at the end of the day the actual network policy, the network rule. So we'll select one of the CILIUM, let's say this one, and we do a CILIUM policy trace. Between a source, and the source is expressed, for example, with this. You can have a look at the CILIUM documentation, which is quite good and quite, let's say, complete in that side. So the source is expressed by first the namespace, and then the name of the pod you want to try as a source. Once done, I will tell about the destination. So the value for the destination argument is this one. And similarly, I'm writing down the namespace of the pod, and then the actual pod, which is here. And if I want to test a level 4 type of rule, I will write down the ports, which is 5601 in this case. I'm executing that. And what he's doing here is trying, the network policy that I've configured for Kibana. And as you can see here, we have all the details. He goes to the network policy, trying the match level. So first, he'll figure out to which pods this policy should be applied to Kibana. And then he will look at all the labels that I've included in the ingress rule, which is related to labels, related to namespace. It's quite important to have a look at this one. This one is the namespace, which is specific, so it's a label that is specific to CILIUM. So that means that for this to work, you need to have your Nginx ingress labeled in a proper manner. And So he first tried the layer 3 level of the rule, and then move to the ports, and then conclude with the verdicts either denied or allowed. So here is a proof that this rule is enforced and allowed. With that, we have finished the second part of our demo today, and we have touched how to leverage network policies to first restrict traffic between pods with this WordPress application example, and restrict the external traffic thanks to this multi-ingress controller example using Kibana as an application endpoint backend. Now let's see how network access monitoring, for example, implemented with Linkerd service mesh, can be integrated in this secure platform. That will be the subject of the next video of this series. Thank you very much. Hello, welcome. This is the Lab 5 demo, part of the SUSECON Digital 2020 hands-on lab, securing your SUSE CaaS Platform for environments. In this video, we'll figure out what it takes to integrate Linkerd service mesh into our secured environments. For this, I'm connected to the management node of my cluster, and I will use the cluster-wide admin user that we have used during the lab 1. And this demo today is about injecting Linkerd proxy into an application named WordPress, which consists in 2 layers. One web frontend deployed thanks to deployment, and a myriad database backend deployed thanks to a stateful set. It's interesting right now to look at the pod security policy that has been selected for those 2 pods. So let's look at the MariaDB pod, and the other one will be the same. To figure out what is the pod that has been selected for this pod, what is the pod security policy that has been selected for this pod, we need to look at the annotation identifying the PSP, and we see here that it's SUSE CaaS PSP and unprivileged. This is something to have in mind in the following of this demo. Let's now double check what are the network policies that are currently set up in the user namespace. The user namespace is the place where I'm executing all the application at the moment. And as you can see here, there's a default -deny network policy, which is meant to deny all the communication, either interpod or with the external network, either ingress or egress. Here, there is also a set of network policies that are application specific, that are there to explicitly allow the traffic that is meaningful for the given application. We have seen that in the previous lab. Now, what about Linkerd? As a matter of fact, Linkerd has been prepared with default parameters, and let's check together about this deployment status. All the deployments are ready. We can use the Linkerd check command line to further check the environment from the Linkerd endpoint. Okay, everything is fine. Now we need to have a look at the way we will be able to access the Linkerd dashboard. As a matter of fact, indeed, the dashboard needs to be accessed from the outside network, which means, in my case, to configure an ingress for it. That's what I've done with this web ingress, which defines the hosts that I will access to see the Linkerd dashboard. Now, what about the actual injection of Linkerd proxy into my application? For that, it's important to understand what that means. It means that we need first to understand what is this injection about. Linkerd proxy injection actually implements the Kubernetes admission webhook, which is implemented then at the Kubernetes control plane level. That's the first thing to know. The second thing to know is that the injection consists in adding two containers in the application pod. The first one is the init container named Linkerd init that will configure the IP table to automatically forward all incoming and outgoing TCP traffic through the proxy. And the second container is the proxy itself named Linkerd-proxy. To actually inject the Linkerd into the application pod, it's not enough to just do some annotation. You need to stop and restart the pod because the Kubernetes will call the webhook only when it will need to update the underlying pod. So let's do that starting by the backend, the MariaDB backend, and deleting the stateful sets. And we will add, we will inject the Linkerd into the MariaDB stateful set thanks to this type of command where you see that I'm using Linkerd injects to change the manifest of the MariaDB application, and all this is applied thanks to kubectl apply. Once done, we can check the status of the stateful sets to see if it's ready. Not yet. We can have a look at the pods to see what's happening. We see that actually we see no MariaDB pod. That means that we need to dig a bit more on the stateful sets and inspect the stateful sets. Here we go. And let's look at the events. Indeed, we see an event which says that the pod could not be created for the reason that it was unable to validate against any pod security policy. And the reason, the core root for that, the root cause for that, is that the init container, the Linkerd-init that I just talked about, requires two capabilities, netadmin and netrow. So to solve that, a way is to edit the pod security policy that will be used for this pod. And as we have seen previously, this is the SUSE CaaS PSP unprivilege. So we can do a kubectl edit and add the missing capabilities. Once done, we can redelete the stateful sets to make sure everything is clean. And re-inject Linkerd into MariaDB. Now we can check the status of the stateful sets to see if it's ready. Seems that it's not ready yet, but let's have a look at the pods that may be starting at the moment. Actually, yes. We see now that we have the MariaDB, so that means that we have solved the issue that we have just seen. And now we just have to wait the containers to be started into inside this pod. Okay, we have one container ready. Let's wait a bit more for the second one to be ready as well. This is taking too much time, so we need to dig into details about the reason why there's only one container. For this, we will look at the logs of the pods. First, at the logs of MariaDB. Okay, from my standpoint, it seems that the MariaDB is started. Let's now check the other logs of Linkerd proxy. Indeed, there's an issue here, clear, which is about a request that could not be dispatched. So my basic guess is that this is related to egress traffic that maybe is not possible for this pod. So to figure out, let's come back to the network policies that has been defined in the user namespace and find out what is the network policy that is applied to the MariaDB pod. Indeed, this is this one. Let's edit this network policy so that we can check if there's an issue with the policy types. Indeed, we see that is only an ingress policy type here. So we can and we should add an ingress related rule here. Let's do that directly by doing this. And adding that possibility to do egress to anywhere and to adding a policy type egress. Once done, we can watch back the pods and to see if the last container, Linkerd proxy, has been started. Okay, the second one is started. Then we can now take care about the front end by starting by deleting the front end deployments and by injecting Linkerd as we have done for MariaDB, applying the Linkerd inject command. And we come back to the watching the pods to see if everything is okay. As you can see here, we have the old WordPress pod that was there because I was deleted the deployment, and now we have the new one that is now starting. So let's wait a few seconds that the two containers are started. Here we have the first container started, and the second one is now ready as well. So we can go now to the browser and see what is happening. By looking at the browser, we can see the Linkerd dashboard, and in the user namespace, the front end can be accessed, and we can see the details. That's being displayed here. And here we have the live calls of the accesses from the HTTP standpoint. For example, this is something that will come back just after that. And we can have access to the Grafana of WordPress which is displaying at the moment. Okay, and showing that the Linkerd is indeed monitoring the WordPress frontend. So coming back to this part here, this information is trying to be this detailed information related to the accesses to the web application, the HTTP traces, really live calls. For example, if I'm browsing a little bit the application, we'll see that the other accesses will show. And as you can see, that the thing that I've just done is showing that this is starting to be maybe internal information. So you may want to further secure the default Linkerd setup by restricting the capability from the dashboard to see this type of details. And this can be done by looking at the way the role and the role bindings has been set up when you have deployed the Linkerd. And let's have a look at that, because that's quite interesting, because also knowing that will be a way, will help us to set up maybe a restricted usage of the access of the Linkerd resources. So looking at the cluster roles that are available for Linkerd, we can check that right now. Cluster roles and grep Linkerd. We see that we have this set that has been, let's say, created when Linkerd has been installed. As you can see, the one that is of interest would be this one, the Linkerd tap admin. That is the role that gives the capability to watch the details. We can inspect it. To see indeed, how you can see that it provides the capability to watch everything under tap in the Linkerd resources, and that's where all the, let's say, the live monitoring, the live tracing information is put. In terms of role binding, to understand to which this cluster role is bound to, we can have a look at the role bindings connected to Linkerd. And the one of interest is this one, where, as we see just right now, the web front end of Linkerd is connected. So let's write that completely. As you can see here, this connects the cluster role that we have just seen, providing this capability to watch the tap live data to the Linkerd web. So, which means that if you want to restrict this capability from the dashboard perspective, you can simply remove this cluster role binding. So But for this demo, what I would like to do is more to come back to my user into my user namespace uh, um, environment, and I would like to restrict the capability to first to provide the capability to see this information to the user admin of my user namespace, but to restrict this capability to really this namespace. And for that, what I will do is I will create a role binding that will connect the crystal role of Linkerd tap admin to the group Kubernetes-admins, in which I have my user admin, as we have seen previously in the previous lab, all this being in the user namespace. Once done, I can change the security context to the user admin and switch the context. And now I can try to access to the Linkerd resources. So as you can see, this is working, and I can try on another namespace. So let's say Linkerd namespace itself. We see that this is not possible. And for the actual Linkerd tap command, the way for user name such as user -admin to do to see the live information would be Linkerd tap on the front end, for example, the deployment front end, and for sure specifying the user namespace, the namespace name. And here, as you can see, it will be able to really see the information. But as I mentioned, since it's as I mentioned, only for the user namespace. So this is a way to provide this capability to an admin, but really in a controlled manner. So as we have seen in this lab, we have touched on how to adapt the role-based access control, the pod security policies, and also the network policies to enable the service mesh for such as Linkerd for our application. And this allows to monitor our pods and to monitor the traffic through the pod. This is our last demo of the SUSECON 2020 digital event, securing your SUSE CaaS platform demo series. Thank you very much for your attention, and I hope that you have enjoyed spending some time with me. Thank you very much, and goodbye.